So when we're talking about the limit of a sequence, okay, we mean that a sequence, an, has limit L, and we'll use this notation, the limit as n goes to infinity of an is L, if we can make the terms of an as close to L as we like by taking n sufficiently large. Okay, so that means that thinking about your list of terms, that far out in the list, for a large value of n, you'll be getting closer and closer to a particular value L. Okay, so here's the terminology that goes with this. If the limit as n goes to infinity of an exists, okay, as a finite number, we say the sequence converges. So remember, just like with our improper integrals, we said that the improper integral converged if the limit that was equal to our improper integral was existing as a finite number. And then otherwise, we say that the sequence diverges. Okay. So this theorem talks about how we can use the limit of a function to find the limit of a sequence. This is saying that if the limit as x goes to infinity of f of x is L, and f of n equals an, okay, so that means that we can think about our sequence points as being basically the subset of a function. So, I was drawing something like this for my sequence, but maybe that's some subset of a function whose limit we can find. Okay, so if the limit as x goes to infinity of the function is L, then the limit as n goes to infinity of our sequence an will also be L. Okay, so this is what allows us to use all the properties that we had for dealing with limits of functions and apply them to the limits of our sequences. Okay, so this just summarizes the limit laws that we have for sequences. I wouldn't think about having to memorize these per se, because these laws should be familiar from dealing with functions, and they're also sort of what you would expect to be true for the limits of your sequences. They shouldn't be too surprising. Note that these laws are specifically for convergent sequences. If you had some individual sequences that both diverged or one of them diverged, then you could kind of have some weird stuff happen when you start looking at limits of their sums or differences or products or things. But if they both converge, then the limit of the sum of those sequences could be the sum of each of the individual limits, or the limit of the difference is the difference of those two limits. If we have a constant times our sequence, we can pull that constant out in front of our limit. Limit of a constant is still a constant as n goes to infinity. Limit of a product could be the product of the limits. Limit of a quotient is the quotient of the limits, as long as that denominator is not 0. And then if we have things like the limit of our sequence to a power, we can bring that limit inside and have the limit raised to the power, as long as we're dealing with some positive powers here with our sequences greater than 0. Okay. So remember, that's specifically for convergent sequences. But in the upcoming videos, we'll look at applying these limit laws to some basic sequence convergence problems, and then we'll introduce a few more theorems and do some additional examples with sequence convergence. So for our first example, we have the sequence given by an equals 3 plus 5n squared all over n plus n squared. And we now know that the definition of sequence convergence involves what's happening to the limit of the nth term as n goes to infinity. So to answer this question about whether this sequence converges or diverges, we're going to need to compute the limit as n goes to infinity of my nth term. So I have the limit as n goes to infinity of 3 plus 5n squared all over n plus n squared. And then I know that I can use the same kind of techniques that I did for taking limits as x goes to infinity for taking my limit as n goes to infinity of the nth term in my sequence. So here, since I am doing a limit at infinity, I can use the technique of dividing by the highest power that's in my denominator. So I could divide the numerator and denominator here by n squared. So I have the limit here as n goes to infinity of 3 over n squared plus 5 all over 1 over n plus 1. And then I see that 3 over n squared and 1 over n would be going to 0 as n goes to infinity. So my limit is equal to 5. So I would say that this sequence
of an here converges to 5. And in fact, we actually have a general rule that whenever I'm going to have a limit as I approach infinity, in this case the limit as n goes to infinity, if the highest power of n is the same in the numerator and denominator, then my limit will just be equal to the ratio of the coefficients of those those highest order terms if they're of the same degree in the numerator and denominator. So you don't have to show this work, but we wanted to see how we could justify that that limit was equal to 5. So what about for this next example here? I'm interested in determining whether the sequence given by n cubed plus 2n over n plus 1 converges or diverges. So remember, there's different ways that a sequence can be stated. Here, we're given it in the form an equals what the nth term is. Here, this is giving you the nth term in curly braces. So that means the same thing. But to determine sequence convergence, again, I have to take a limit. So I'm taking a limit as n goes to infinity of n cubed plus 2n all over n plus 1. So I do have a higher power of n in my numerator than in my denominator, which should mean this is going to infinity. But I'm going to go ahead and use the trick of dividing the numerator and denominator by that highest power of n that appears in the denominator. So dividing everything by n here. So I have n squared plus 2 all over 1 plus 1 over n. So I know that 1 over n is going to 0, just like these terms here were going to 0. Okay, n squared, then we'll be getting bigger and bigger and bigger. We're adding 2 to that. So this is going to be going to infinity. So here we would say that our sequence of n cubed plus 2n over n plus 1 is diverging since that limit went off to infinity. Okay, so what about for this last example? Here I'm interested in determining whether the sequence whose nth term is tangent of 2n pi all over 1 plus 8n converges or diverges. Again, we need to look at the limit of the nth term as n goes to infinity, so I need to compute the limit as n goes to infinity of tangent of 2n pi all over 1 plus 8n. Okay, so here notice that what I really want to look at is what's happening on the inside of that tangent function. What's the limit as n goes to infinity of 2n pi all over 1 plus 8n? So let's look at that separately here. The limit as n goes to infinity of 2n pi over 1 plus 8n. Notice that the highest power in my numerator and denominator is n. So highest power is n to the first in both cases. N to the first power, here I've got highest power is n to the first power. So I know that my the value of my limit there is going to be equal to the ratio of the coefficients of those highest order terms that are the same in the numerator and denominator. So that limit will be equal to 2 pi all over 8 or pi over 4. Okay, since tangent is defined at pi over 4, this limit is going to be equal to tangent of pi fourths, which we know is equal to 1. So in this case, this sequence of tangent, or the sequence whose nth term is given by tangent of 2n pi all over 1 plus 8n, converges to 1.